And so now we're ready for our first major topic of analytical chemistry. So we recall that the main point of analytical chemistry is to address two questions. What do we have, and how much do we have? And the way that we do that involves acids and bases is through a titration, which you should remember doing, but we're going to cover all of the points about it and how we use it to answer those two questions, which is a bit different than what you would have learned about in general chemistry. But before we can even touch the titration, we need to make sure that we know all of the basic groundwork that relates to acids and bases. And that takes several lectures to do. So let's kick things off with a brief review of some definitions. I don't recommend writing anything on this slide down. We learn it through just constantly using these concepts. So there are numerous definitions of an acid and a base. These are the two that you would typically learn about in Gen Chem. In organic chemistry, you would also learn about Lewis acids and bases, which we're not going to discuss. In fact, in this class, we will limit our definition to the Bronsted-Lowry definition, where an acid donates protons and the base accepts protons. Now, when an acid is placed in water, it doesn't just donate a proton that hangs around and does nothing. That proton will always find one of the countless water molecules it's surrounded by, and the two will bond together to form hydronium ion, H3O+. This always happens in water to the extent that proton and hydronium ion terms are basically used interchangeably, even though they are technically different things. One more time, this never technically exists by itself in water. You will always have this, but often we will just write H plus to keep things simpler, but we should know that it's never really H plus. It's always H3O plus because the water will always bind with the proton. At first, I will go with the technically correct hydronium ion, but then later I'll use the simpler representation of just the proton, as we'll see. Now, if an acid and a base meet each other, they will form a salt. This is an ionic compound, usually a strong electrolyte. So for example, if we have a weak base like ammonia, and it meets a weak acid like nitrous acid, the two would come together to form this compound here, which we would call a salt, and then that would 100% break apart into NH4 plus and NO2 minus. And so this salt is more like a middleman, and we'll just cut it out because effectively what's really happening is these form these, which is what's written here. And we call these products a conjugate acid conjugate base pair. And there are a couple of ways that you may have learned to define these, but the way that I see it, the conjugate acid and base are just the acid and bases from the reverse reactions point of view. If we think of these as the reactants, we can see that NH4 plus loses a proton to become NH3. In other words, it's a proton donor, it's an acid. NO2 minus is picking up that proton and becoming HNO2. In other words, it's accepting a proton, it's acting like a base. And so again, the conjugate acids and bases are just the acids and bases from the reverse reaction point of view. And if you have an acid and a base getting together, there will always be a conjugate acid and base pair formed. Now, the next part of our review is so important that I'm going to write it down, even though technically you've learned all of this in the past. We're going to discuss the autoprotolysis, or sometimes we'll refer to this as autoionization. Autoionization of water, or H2O. And this is what happens when water reacts with itself. So H2O molecule meets another H2O molecule, and then forms H3O+, our hydronium ion, and hydroxide ions. And this only happens to a very small extent before those hydroniums and hydroxides start reacting backwards to reform those two waters and an equilibrium is reached. Let's specify our states. The water is liquid, and we can think of the H3O plus and hydroxide ions as being solutes that are in that liquid. And so if there's an equilibrium, there must be a K value associated with it. And we give this K value a special subscript, W, to indicate that we are talking about water. Particularly, we call this the water dissociation constant. Water dissociation constant. And the reason that we call it that is because if we were to use our shorthand for the reaction we wrote earlier, we could think of this as just H2O dissociating into H plus and hydroxide ions. But we know that H plus will not exist by itself in solution. It would find the second water and become H3O plus. And so notice that when we look at the full reaction here, water is really behaving both as an acid and a base. One of the waters is accepting a proton to become H3O plus, so that water we would say is a base. The other water is in turn giving that proton away, and so it's behaving like an acid. We call water an amphoteric species. It can react both as an acid or a base. The book uses the term amphiprotic, which in this class is effectively synonymous, although there is a subtle difference between the two, but it's not relevant in this course. And so this equilibrium constant's value is 1.0 times 10 to the minus 14. And we'll make a note that this is only true at 25 degrees Celsius. But we will always assume that that's the temperature in this course unless otherwise stated. Another note we should make: this always applies in aqueous solution. Always applies in aqueous solution. Let's underline the word always. We'll see why that's such an important point momentarily. But this Kw for the reaction that we've written above, the autoionization or proteolysis reaction, would just be equal to H3O plus, or if we did shorthand, we could write that as H plus. For now, I'll be totally correct. H3O plus concentration times hydroxide concentration. And I'm just following the standard rules for writing a K expression just for this particular equilibrium. We have our two aqueous products. They have no coefficients, or their coefficient is 1, so we don't bother writing any exponent here. And then what would go on the bottom are the reactants, but our reactants are liquids, so we don't include them. And so there's nothing special about the rules for this K. Much like the KSP, the subscript just tells us that we're talking about the K of a very specific equilibrium. Now, because everything here is 1-to-1, we can see that if the only reaction that's occurring is water reacting with itself to form these two species here, we will form equal concentrations of both of these. And so these two values should be equal and multiply together to give 1.0 times 10 to the minus 14. And those numbers would be 1.0 times 10 to the minus 7. 1.0 times 10 to the minus 7. We know it's got to be units of molarity because they're aqueous species. And we'll add the word each, just to make it clear that each of those concentrations is that number. And we'll also add the note that this is only true for pure water. In which case we have what we call a neutral solution. If we were to then place an acid in the water, that would tip the balance, and we would get what's called an acidic solution. And in this case, we would now have unequal concentrations of H3O plus and hydroxide, and as you might guess, we would have more hydronium ions than hydroxides in an acidic solution. On the other hand, a basic solution will just go the opposite. H3O plus concentration will be less than the hydroxide concentration. But in either type of solution, whatever these concentrations are, they'd better still multiply to 1.0 times 10 to the minus 14, because this Kw always applies in aqueous solution. And we'll see why that is in a later lecture. After that comes a clicker, which just tests to see if you can figure out, is this solution of that concentration hydronium ions acidic, basic, neutral, or...
Scrum-diddly-umptious.
And while we'll do it in Zoom, I'll give you a hint. It's not D.